We're ready to restart. Do you hear me? Thank you. A few words about how the DNS and the names are organized. At the top level, there used to be a California-based company that was still around, but has been under international pressure, forced to give away the control of the names to an international organization, which is called PTI, which does it for ICANN now. This is very complicated, the real law and legal relation between all those entities. But at the top level now, there is an entity which is controlled by an international organization that allocates the top level domains here. Now, this is just about the allocation of the names. The allocation of the name says, for example, imagine the company called UBS would like to buy the domain UBS, so they have to go there. And if there's a dispute, if another company wants to buy it, then this will be settled at this top level. A different thing is running the DNS server. So this is done by a number of other competing companies. At lower level, we have the same dichotomy between the two. We have what is called a registry, which is the legal entity that owns the right to allocate names. In Switzerland, it is Switch, which is also the ISP for the universities. In the past, the registry was also the entity that would sell the names. Now it is separated. The entities that can sell the name are any entity who sell computer services like Infomaniac, Switch Plus, etc. So those are formally separate entities. So if you want to have your name, your family name.ch, you have to buy it from this, and they will ask you for a fee for every year where you have it. Once you have that, you still don't have a name that works because you need to put it in a DNS server somewhere. So if you're a big company, you have your own DNS server. Otherwise, you need to pay some company that runs DNS service. Infomaniac does it, for example, but it doesn't have to be the same from whom you bought the name. So you have to put your name into a DNS server. Once you have that, all those steps, then you can use your DNS name. There's an attempt to bypass entirely this hierarchical organization in the philosophy of blockchain technology. It's called Namecoin. I'm not sure if this will be very successful, but the .bit domain, top-level domain, is reserved for that. And much like you can use the blockchain technology to do money transfers without going through a hierarchical system of banks, then you could agree on who owns what name and what is the IP address that corresponds to it using this technology. As I said, not sure whether this will be very useful, but I may be wrong. We'll see in the future. DNS is indeed used not just for a convenience to replace IP addresses or other things by more human readable things, but the fact that now before going to any site, we first go to the DNS means we have one level of indirection. And this level of indirection can be used, for example, for a number of features like load balancing. Load balancing is, for example, if you're a big company and your name is very popular and you may have millions of users that go to your name. And of course, you will not have one machine that runs this. You may have a large number of machines here. How you do, or even sites. How do you do this? Well, one solution is to use what is called a load balancing DNS server, where you would map your name to a number of other IP addresses or canonical names, most likely here, with very short time to live here. And you can, then your DNS server can change this depending on the information it gets from the load management system in the different data centers. So it gives as priority one this one here, but it may change the priority. And also in the response that a client will receive from such a server, you may change the order depending on the IP source address, for example. to do some load balancing that is also based on the source addresses here. So this is very frequently used and is one of the important uses of the DNS today by large companies here. This is how also, if you can check it, if you do a dig to Google, you will very probably find very small TTLs here. The way I've presented DNS runs on UDP and has no security. Of course, as you can imagine, it's very easy to manipulate, to do attacks if you have complete control of the names here. So there are two ways this is addressed today. The first way is to have DNSSEC. DNSSEC means that the records are signed using pretty much the same public infrastructure that we have discussed in the context of BGP. So because IP addresses are also allocated by entities that have public keys, then we can sign also, and using pretty much the same system as for BGP, which is called the RPKI, we can verify the signature of mappings here. So some DNS servers of the big companies, they implement it systematically. So if your client verifies it, you could verify this here. Some domains also implement it systematically. So that one first part of the problem, where the domain names, that the mappings, the records that are originated by the owners of the record are signed. And if you get something that has been corrupted, for example, if somebody has changed the IP address that corresponds to epfl.ch in order to do an attack on epfl, then the signature will be incorrect. And so that is how you can verify. There's another level of security that can be added. It is, instead of running DNS over UDP, you can run it over TLS or over QUIC. So therefore over TLS and over TCP, or over QUIC, because QUIC essentially is the same as TCP and TLS bound together here. So this is typically done by clients in enterprises that want to, when you go to the enterprise server, DNS server, you want to be sure you're going to an authenticated server and not to another machine that might be incorrect here. So this is another alternative, and the both in some sense are complement. This is typically used to make sure that the client goes to a local server that is trusted, and this is used for your local server to get verification of the mappings that it has obtained over the open internet. At home, you probably use names that don't use DNS servers. There are two techniques that all belong to what is called the zero-conf paradigm. Zero-conf is a set of protocols defined by the IETF to make things plug and play. So if you start your printer and you give it a name when you boot your printer here, any computer in your environment will see the name of this printer. And so this corresponds to a domain, the .local. The .local is typically not implemented by having a DNS server putting the names here, but is done by a protocol that uses multicast. Originally it used broadcast, but here it's multicast, where essentially if a printer has this name, it will simply broadcast to everybody using this multicast address the name that it has once in a while. And then if your computer is trying to discover printers, then it will see this message once in a while. Of course, this works only inside a LAN, so inside a subnetwork. We don't use that type of information to go to the open internet. So this typically is limited. Those are broadcasts that are limited with TTL = 1. So it is used to discover devices, but also to resolve names. If your computer is programmed to print to this name, then if it doesn't know what's the IP address, it will send to this multicast address who has this name, and if the printer is up and running, it will respond, and only then you can send your information to the printer. So this is what is called the Bonjour protocol that was made the success of Apple and Apple Talk at the beginning. Before that, systems that don't have this, it was a nightmare to configure your printer. You needed to know the IP address and everything, and if you don't have it correctly, you cannot print here. With this, that's automatic. There are things that are similar. UPnP is typically used for TVs, for your, if you have a server at home where you have all your music, then a similar protocol will be used, and you will see the name of the machine or of your TV. The way it's done is, again, by using broadcast, not by using the DNS. So those are serverless DNS instances. Voila, time for a little quiz. We've seen that the DNS is not a real database in particular. The difference between the DNS and a database is that there is no consistency of the records. We don't go to the database to check what is the name, but we look at the cache. We go to the original file only if we know nothing. And the results that the changes are not instantaneous. They are not synchronized here. For example, if we change the IPv4 address of this service here, how long will it take for the whole world to be informed of the change? Will it be instantaneous, or will it take some time? I close the poll in a few seconds. And you see the results of the majority that says C, which is the correct answer. I said something wrong an hour ago. I said the PFL names of TTL 2 days, but it's 1 day. Here, this value corresponds to 1 day. So this will be cached by everybody, but the value here will allow us to stale the cache after 1 day. Well, the downside is that if you change your name here, it may take up to 1 day, in that case here. It may take less if the value that was cached was recovered some time ago, so that the value that you have is 1 day minus the time that has elapsed since you first visited the cache here. But that's the big difference with the database system. It is not synchronized. Big data, big companies will have DNS names with TTLs that are very short, order of a few minutes or even a minute, which of course means that the traffic they will have on the DNS server will be huge. So the price to pay for that will be to have an infrastructure for DNS that has the appropriate performance here. We see one use of DNS, which is to really have some dynamic mapping that is completely different from the original use that was intended. The next topic is something that is most of the time completely invisible to us, and is called application layer gateway. An application layer gateway is something that should not exist if we adhere to the original philosophy of the internet. It's an example of a middle box. Here is an example, which is a web proxy. Sometimes when you go to the web, you don't go directly to the final server, but you go to an intermediate machine that will get all your messages and repeat them to the final server. So this is a proxy. It's called a proxy that is on the client side. It's proxy in the sense, we've seen that word several times, we'll see it again. A proxy is something that pretends to be the other end. So it hides to A the fact that it is not B here. Here, such a proxy will terminate the TCP connection. So if we use TCP here, when we send a HTTP request here, or whether over TLS or not, then the message will be completely read and interpreted by this intermediate system here. that most of the time will do nothing else than simply repeat it to the other server, but might also do something about it. It might change the content of the reply that is obtained here. So this is an example of an application layer gateway. Why is that done? Well, some web proxies are done for caching here. For example, some companies implement caches with the idea that a lot of static content is required by many users. So if user 1 requested from the remote destination, the cache may store it. So here we cache the file here, which can be here an image, but could also be a video. And then if someone else gets it, you will get it from the cache instead of getting it from the final destination here. Of course, there is in HTTP, there are extensions to manipulate this, and in particular, there are also time to lives in the HTTP protocol and capabilities to, for example, ask something if modified since, in order to make sure we get the new object only if it has been updated since the last version here. So this is no longer much deployed at EPFL as far as I know, but similar systems are deployed in content distribution networks. So when we do this PC here is not at all going to the final destination. That's an example of a web proxy. Today, most of the traffic on the internet hopefully is using TLS. So when we use TLS, the web proxy, which is in that case called performing an HTTP tunnel function, will do things in a slightly different way. In what I said before, we were simply terminating completely the TCP connection. So in order to terminate the TCP connection here, there is a problem if the cache, if we're using TLS, because now the certificate here that was given by this guy cannot be signed by EPFL cache here. So this will not work unless both are in the same entity here, or if the data that we have, we accept that it's not secure here. There is a modification to the protocol of HTTP that allows to support actively the tunnel, where first we set up a TCP connection and my web browser in that case, which is not the case at EPFL, but is very often the case if you have machines that are configured to work in companies in intranet. Your web browser will be configured to go to a web proxy. It will never go directly to the outside internet. And whenever you do a request, you will first do an additional HTTP message, which is called connect. Instead of going to the, you first go to the web proxy, and then the get function instructs the web proxy to go to the remote destination where TLS can be done here. So the TLS encryption will be done end-to-end between you and the final destination here, but the connect will go via your web proxy. Why do we do this? Well, the first motivation in companies is to allow or not allow here. Here in clear text, we know what is the destination, and the HTTP proxy may refuse to send you to the destination. That's one of the major functions that can be done here. Once it has accepted, there is not much it can do because the communication will be encrypted. So it will not be able to modify the communication, but it may be able to allow or not allow it. There is another side effect here, which is that we have now two TCP connections. Lisa opens a TCP connection to the HTTP proxy, and the TCP proxy opens a TCP connection to the remote destination. And the only thing that the TCP proxy will do is to pipe the data from one connection to the other once it has accepted to let it go here. But there's a difference in terms of performance, which also justifies the use of such HTTP proxies. Because here we have two TCP connections, and we know that TCP has performance problems, in particular related to round trip. So if Lisa is over a Wi-Fi network, there might be a loss rate which is not negligible. And if we know that if we go over the internet with a large loss rate and a large RTT, round trip time, the performance of TCP will be very bad. TCP will interpret every loss due to Wi-Fi as a congestion loss and will give you a very small window. Here it will do the same. It will do the same, but your small window will be over a very small round trip time. So if your round trip time is millisecond, even with a small window, you will get 100 or megabit or more of useful throughput. And over the long distance, where you will have the long RTT, presumably here you do not have such wireless losses here. So that's also another motivation for doing this. I've given examples of application layer gateways. We will see another motivation in a few more minutes. But first, let me state that in principle, we would like to avoid them as much as possible. That's not the philosophy of the internet. And the major philosophy was to simplify the network. The network is independent of applications. It's hard enough to move from IPv4 to IPv6. So if we put intermediate systems in the network that are application dependent, of course, whenever we change the application, it is difficult. Also, we've seen in the very first week that store and forward is not good in terms of performance here. So that's the principle. The end-to-end principle says, don't do application layer gateways. But we've seen an example with an HTTP proxy. Another example that we use all the time, that we're using now with Zoom, for example, that's for the semantics issues. Zoom merges n video streams into one and does it on servers. Here's another example. When we send emails, I send a mail using SMTP and other protocols here. I connect to my mail server connects to your mail server, and you connect to your mail server to obtain the information. What would happen if we would strictly apply the end-to-end principle? Well, my computer will connect directly to your end device to send the mail. It's possible. It's quite possible. In particular, if you have a Linux PC, you can run a mail server here, give me your IP address, and I can program my mail program to send you the mail directly. But of course, nobody does that for lots of reasons. Security first. You don't want to be connected by anybody. Although this may be a good security measure to exchange mail in a highly confidential environment, you could do that over TLS connections, and you will be sure you receive mails only from people who have authorized computers. But most of the time we don't do it because of mobility. You don't want to have your computer running as a server. You want it running as a client, and you interrogate your server that does the job for you. So commodity, mobility are reasons for avoiding that here. I mentioned the HTTP tunnel. That's an example of what you get when you connect to a company network, for example. You will do security and access control here. A special form of application layer gateway is very, very frequently used. We've seen the HTTP tunnel, which are client-side proxies. We can do the same on the server side, and most data centers do that for various purposes. One purpose, which is complementary to what we saw a minute ago with DNS, is load balancing. With DNS, we saw that we can do load balancing across sites. Typically, we also want to do load balancing inside a data center. A data center, as we've discussed several times, is just a big room with lots and lots of servers. And when a request for service comes, you want to allocate it to one server. So typically, servers are not directly accessed, but instead there is a machine that serves as a firewall, but also as a load balancer that is visible to the outside. So when Lisa goes to a service at whatever her preferred company is, she will not go directly to the service, but her interaction with TLS and HTTP is intercepted by a machine here that will then decide to forward it and will do the piping to another machine that is one of the machines here. And here there will be an algorithm inside the data center to decide which machine to send it to. Of course, you would like not the load balancer to be a single point of failure, so you would typically duplicate or even triplicate it here. How would you split split the traffic between different load balancers. Well, I mentioned the DNS, but the DNS is used typically across sites here. What is very often done is equal cost multipath routing. When Lisa is sending a request here to this center, this has an IP destination address, and the routing infrastructure in this data center can use equal cost multipath routing with the same IP address given to the two load balancers here. So there will be two equal cost paths to go to the destination, and the routers, as we have seen when we discussed OSPF, will split the traffic to one or the other. So this is one of the typical solutions. So we use the routing infrastructure to split the traffic here, and therefore there will be hopefully even a distribution of the work between the two. And if one of the machine goes down, then hopefully the routing protocol will be made aware of that and will do the equal cost multipath to the machines that are working here. So that's another example where application layer gateways combined with routing are useful here. I mentioned firewalls several times. Company firewalls typically use all the examples we gave before, an HTTP tunnel, which is a web proxy, perhaps a load balancer here. And most companies have what is called large firewall infrastructure, which is a zone, which is called sometimes the DMZ, the demilitarized zone, which is an untrust zone, which is the zone where the servers are that are allowed to talk to the outside here. So EPFL, like all companies, have that. So when a request goes to an EPFL server, it might go directly to one exposed server, but if it goes to an internal server, it might go first to an inside server here that will play the role of application layer gateway. Why do we do that? Well, because those systems are exposed to the outside, so they need to be very, very cleanly maintained and monitored, and perhaps all of EPFL cannot be monitored in the same way. So typically also this is combined by filtering routers. We've seen that routers do not simply do lookup based on longest prefix match, in particular the routers that are at the boundary between companies or home and the other networks, but they do filtering based on rules that may deny access. For example, typically here, traffic that comes from the outside of EPFL to EPFL is allowed only to servers that are put in this untrust zone. So much about application layer gateway. A little quiz to make the transition. Assume Lisa goes to this preferred service here. Oops. Can we have a poll, a new poll? Stop sharing. Okay, relaunch polling. Okay. No, that's end polling. Close this one. Could we have a new poll? Thank you. So Lisa goes to this data center, and a packet is lost on the internet between Lisa and the load balancer. Which system will retransmit it? I'll close in a few seconds. And the majority says A, which is the correct answer. So the important thing about load balancers, application layer gateways, and HTTP proxies, is that they terminate the TCP connection if we use TCP. If we use QUIC, it will be the same. They will terminate the QUIC connection and start a new one here. As a result, if a packet is lost, the load balancer will detect it and retransmit, which means that the load balancer must be a powerful machine able to handle a lot of TCP connections. And this exists today. So some machines have been specialized into performing, serving a large number of TCP connections with a fairly simple logic. So a load balancer doesn't have to do complicated database queries, for example. Oh. Okay, do you hear me now? Do you hear me now? Yes, okay. Broadcast of and answers of yes. So I was saying that the load balancer therefore has to handle a large number of TCP or QUIC connections, and there are machines that have been specialized in doing this. So they are able to handle a large number of TCP connections, but of course they are not made to handle a complicated application logic. So they don't have a database system. This is why we separate the two. Application layer gateways are important also today in the context of the interworking between IPv6 and IPv4. But before discussing that, let's discuss some side effects of the fact that we have IPv6 and IPv4. You are aware of this through lab 3. In lab 3, we did a client that had to test whether a server is working on IPv4 and IPv6. We've seen how to do that. So, of course, today, most modern machines run IPv4 and IPv6, but not all servers run with IPv6. For example, for some reason that is not entirely clear to me, InfoScience runs only on IPv4 at EPFL, right? Even though EPFL has IPv6 everywhere on the wired network here. So this is probably because of legacy systems, stupid things like IEEE Explore validates that you are on EPFL network by looking at your IP address, and it does it with IPv4 address. So those are legacy problems. Some systems use the IP addresses for a number of things, and if they move to IPv6, they have to change their code. So legacy systems will disappear sooner or later, but they have a long life. They have a hard time disappearing. There will be also non-legacy systems. In the worst case, you will have systems that have only IPv6. Presumably, if you run a server somewhere, if you're a big company, you will insist and work very hard to have IPv4 addresses, but sooner or later, new stuff will have only IPv6 addresses here. And then you will have the fortunate things like us at EPFL, where we have as many IPv4 addresses as we want, and as many as IPv6 addresses as we want here. What will happen when we have this and that? So, for example, if I have a machine that runs v4 and v6, and I connect to a machine that also has v4 and v6 here, what will happen? Well, most of the time, machines will prefer v6 because they will say, if I have both, I prefer the modern rather than the old one. So if that's the case, Lisa will connect via IPv6 to the server of EPFL here. But how does her machine know that the other end has IPv6 or v4 or both here? I close the poll in a few seconds. As you see, the majority says B, so you would try a V4 and V6, which is probably not the correct answer. Why is it probably not the correct answer? Well, because remember from your lab 3, before you go to this site here, you will not directly go there. You will do something. You will do get host by name or something like this. What does get host by name do? It goes to the DNS. So you will first go to the DNS before going there. Since you go to DNS, perhaps it's a good idea to ask the DNS about both IPv4 and IPv6 address. So if you're a dual stack machine, your application, presumably, of course, it's like in lab 3, you can write an application and will not do it. But most applications today will first check the DNS, and they ask the DNS, what is the IP address of this? And it's simple to ask both here. So you will get this. If you get only an IPv6 address, then you know you must use IPv6. You have no choice. Of course, you need to work with a DNS server. DNS as an application is completely decoupled from the transport. So you can configure your machine with a DNS server IP address, which is an IPv4 address, and still use it to obtain IPv6 address. So there is no dogmatism here. A DNS server can use IPv4 transport, even if it's used for IPv6 queries here. So little detail to check here. Last, let us discuss what is probably the most annoying things with IPv6, the IPv4 and IPv6 interworking here. This is a topic that we will discuss today and next week when we discuss other technologies like tunnels and address translation. So as we know, IPv6 and IPv4 are incompatible. If you have a v4 only host, you cannot speak to it. And if you have a v6 only host and vice versa. So if you speak languages that are not understood here, as this cartoon is illustrating. And this is a major problem for all operators here. Fortunately, there are solutions, and we'll see what those solutions are. In order to understand the solutions, it's perhaps important to attempt a classification of the problems by making the difference between interworking and access. Interworking is if I have an IPv4 machine, IPv4 software or hardware that works only with IPv4, and it wants to talk to another machine that works only with IPv6. How can I solve this problem? This problem is called interworking. An example here is, for example, if you are in a part of the world where you receive only IPv6 addresses, and you still want to go to InfoScience, right? How will you do that? EPFL doesn't provide IPv6 access to InfoScience, so how will you do this? That's the interworking question here, where application layer gateways can be used. We will see another solution next week here. Next week, we will also discuss of another problem, which is sometimes very different, sometimes related to this one. It is access, and what I call like-to-like access. Like-to-like access means if I have an IPv6 machine that wants to talk to an IPv6 machine, but there is only IPv4 between the two here. For example, that would be the case if you have only IPv4 from your internet service provider, like, for example, the Wi-Fi of EPFL today provides only an IPv4 service. And if you want to do the IPv6 lab, you have this 6-to-6 over IPv4 infrastructure. So that's the problem you have when you are modern and the network around you is old. But you will also have the reverse problem if you have software, for example, some software like Skype, as far as I know, doesn't handle IPv6 very well. And if you have only an IPv6 access, which is coming in some parts of the world for cellular networks, where they don't have enough IPv4 addresses, so they will give you only IPv6 addresses. So those problems here are easier to solve, and we'll see also next week how they are solved. This, as usual in TCP/IP, everything is never too strict. There is a gray zone between the two. You can use a solution to like access to solve the interworking problem. For example, if you have an IPv6 only host that want to connect to InfoScience, you can put IPv4 into it with no IPv6 access because you have only IPv6 software, and transform your interworking problem into run your application over IPv4, which is typically easier to do because it's only a software program in your machine. So find a version of your browser that works for IPv4, and then go to the IPv4 web server over some solution to 424 transport over IPv6. Today, we will speak of interworking. And of course, a completely trivial solution is to use a web proxy. If I want to go to a web server like InfoScience, for example, and EPFL says, oh, I don't want to move InfoScience to IPv6 because I don't know how to do that, then one way to do it is to do a web proxy, for example, some kind of tunnel. That would be this example here, you put on the client side. And whenever I want to go to this server, in reality, I go to the web proxy, and the web proxy can simply do sophisticated things or can pipe all the information from one TCP connection to the other. You can do that on the client side or on the server side here. So both can be done here. How do you know you have to go to the application layer gateway instead of going to the final web server? Well, as you can imagine, using the DNS here. So if you do server-side proxy here, you can put in the DNS a different address for this service, epfl.ch, over IPv6 and over IPv4. So over IPv4, you will give this address. Over IPv6, you will give that address. So that's a trick that was done until recently, for example, by the standard EPFL services that were moved to IPv6 in this way. So you don't really change your application logic, you just simply make an application layer gateway that will pipe all the output of your TCP connection to another TCP connection going here. One is over IPv6, the other is over IPv4. Of course, if you use the DNS correctly, people who have IPv4 will go directly to the remote destination. They will not need to use the application layer gateway. The same will be, the opposite will be true if we have only IPv6, we will go to the application layer gateway here, through the DNS redirection. An interesting question is what will happen to dual stack machines. Lisa has a dual stack machine that has both IPv4 and IPv6. Will it go to the application layer gateway or to the final system here? I close the poll in a few seconds. Most of you say it depends, which is very wise and is probably true. Let's analyze what will happen. Lisa will go to the DNS and will find two addresses that work. So then the software here has the choice. It can use a socket that will use IPv4 or IPv6. What it will do depends on the optimization that is done by Lisa's computer. Many systems that I've seen have a static rule that says if you have both, prefer IPv6. If that's the case, Lisa will go via the application layer gateway, which will be suboptimal because it means we'll go two application level hops instead of one. Many systems, or in the past, the Mac OS system did something different. I'm not sure it still does it today. It maintains, in such a case, it will maintain some quality of service monitoring data. So it will go there. The first time it will probably choose IPv6, and then we'll see whether it finds that the quality is good. The quality will be the loss rate, for example, for the TCP connections, how many retransmissions there are. If it finds that it is bad, it will try IPv4 the next time. So the true answer is, it depends on the configuration. But even if we do optimizations, it may be difficult for the host operating system here to detect whether there is an application layer gateway. It can detect what's the performance of the TCP connection between the two, but whether the application layer gateway is slow, that depends on the application logic and is typically not done by the operating system here. So even in that case, if optimizations are done, we might go through the application layer gateway, which therefore needs to be high performance. Voilà, that's the end for today. We've gone through various aspects of the application layer. A few facts to remember. QUIC can be used as a replacement for TCP. Try it with the commands and I mentioned in the slides. You can test it with Wireshark. You will see QUIC. And for any software that's by Google. So if you use a Google Chrome, for example, to go to a Google site, chances are you will be using QUIC here. QUIC is largely a replacement for TCP. The main differences is that it mandates the use of TLS and it allows multiple streams. We've seen also that in principle, we should never have application layer gateways, but we deploy them for things like security, performance, and also for solving the interworking problem between IPv4 and IPv6. And last, the DNS, which was originally used primarily as a simplification for human readability, is used for also other purposes, for load balancing, for example, and also for managing the difference and in access to IPv4 and IPv6. Voilà. Thank you very much. Take care. Bon après-midi à tous.